Another important application of logic is consistent systems. So if we want to check if a set of compound propositions is consistent, we want to check if there exists a truth assignment to the proposition such that all of the compound propositions are satisfied simultaneously. So the first thing we want to do is we want to check if two compound propositions are consistent, and then we want to add a third to show that the third would make the system no longer consistent. So our two propositions that we're going to consider are P, there was a heat wave in Los Angeles in July 2019, and Q, there was a heat wave in London in July 2019. And our compound propositions that we're considering are P or Q and P or not Q. So the system that we're considering is P or Q and P or not Q. And this is consistent if this compound proposition is true. That means both of those propositions are true simultaneously. So let's look at the truth table. So if P is false, then if Q is true, P or Q is true. But if Q is false, P or Q is false. But when we're checking for consistency, we need both of those compound propositions to be true simultaneously. So this is a problem. You'll notice that if P is false and Q is true, the first proposition is true, but the second proposition is false. So you'll notice that this assignment does not show that the propositions are consistent because they're both not true simultaneously. Similarly, if both P and Q are false, P or Q is false, but P or not Q is true, and since both of those propositions are not true simultaneously, that would not show that these propositions are consistent. Now, let's look in contrast to what happens when P is true. When P is true, regardless of what happens with Q, you'll notice that P or Q is true and P or not Q is true. So in this case, you'll see that both of these assignments, where P is equal to true and Q is equal to true, or P is equal to true and Q is equal to false, in both of those cases, both of the propositions are true simultaneously. And you'll notice that this shows that these propositions are consistent because they're both true simultaneously. We found a truth assignment. However, if we add the proposition not P to those propositions, you'll notice now if we try to satisfy P or Q and P or not Q and not P, you'll notice that now these three propositions are no longer consistent, and the reason for that is this third proposition, because the first two propositions require that P is true, and the second requires P to be false to be true. Okay. Now, let's look at another example to check if a set of propositions are consistent. So first, let's discuss what the propositions are. So whenever the system software is being upgraded, system software being upgraded is P, users cannot access the file system. That's Q is access the file system. So this proposition is P implies not Q. The second proposition is if users can access the file system, that's Q, then they can save new files. That's R, so that's Q implies R. And the third proposition is if users cannot save new files, so that's not R, then the system software is not being upgraded. That's not P. Now, once we're familiar with rules of inference, there are faster ways that we can consider this, but for now, let's just consider all the possible values that we can give to each of the atomic propositions and to check if any of them are such that we can have all three of these compound propositions true simultaneously, because that would indicate that we have a consistent system. Okay, so first I just want to mention again, so what we're trying to show is that we have an assignment to P, Q, and R such that P implies not Q, and Q implies R, and not R implies not P are all true simultaneously. So to do that, let's just consider our three propositions, and those propositions again are P is system software is being upgraded, Q is users can access the file, and R is users can save new files. And now I'm just going to draw the truth tables, and from this we can determine if we have any assignment to these propositions that would satisfy all three of the compound propositions simultaneously. So we have true, true, false, false for Q, and just to make this a little bit easier, I'm going to see if we can satisfy the propositions simultaneously. So the second that we have an assignment that cannot satisfy one of the propositions, we know that will not be an assignment that can show that the system is consistent. So let's just do now. So we have P, not Q, Q implies R, and then not R implies not P. And depending on the author, negation can be the tilde or the little backward L. So this or this you might see. Okay, so now let's consider the first assignment. P implies not Q. So the second that we have true implies false, we know this first implication is going to be false, so we can just stop. This cannot show that the system is consistent. And once again, if we have true implies false, we can eliminate this also. So we've just eliminated two possible assignments, and that is when P is true and Q is true. The first implication would have to be false. So now let's look at the next assignment. So the next assignment is true implies not false, so that's true implies true. So for both of these, this would be true. And we can go down just to check for the rest of the assignments. So if P is false, the implication is going to be true. So for the rest of these, we cannot eliminate any more of these. Okay, so now let's go look at the second implication and the assignment that we have for it. So the next implication is Q implies R. So now when we look at this, wherever Q is false, we know that this implication has to be true. So we know this has to be true, and we can go further down and we know this would have to be true. Okay, and now we can also see whenever we have Q implies R, so true implies true, that's fine. But we can eliminate one row, and that row is when Q is true and R is false. Well, we know that this implication would have to be false, so we can eliminate this row also. Okay, so far it's looking like we have some truth assignments, but now we have to consider the last implication. And this last implication is not R implies not P. So let's consider what we have available to us. So if R is true, not R will be false. So whenever we have R true, we know that this last implication is going to be true. So let's just mark that. So whenever we have that not R, so we know if R is true, not R will be false. And then this entire implication is going to be true because false implies whatever, and we're good. So let's just look at that. So we have the third row, and the fourth row we have to consider, and the fifth, so R is true, and that would be false, implies whatever, so we know that this will be true. And now let's go a little further down, and then we know when R is true, the implication will be false, implies whatever, so that was going to be true. And now we just have to consider the two cases where we have not R implies not P, and R is false. Okay, so here, in this case, so this, when we negate false, we get true. True, negate P is true, implies false when we negate both of those. So this would be false. So this would be a case where true implies false. So we know that won't be good. So we have to eliminate that. And now, finally, we can look at the last example. So we have false, negate that, true implies true, and we're fine. So in fact, we found several assignments that satisfy all three propositions simultaneously, and that is sufficient. So if you found one, you could show that this entire system is consistent, and it just so happens that we found several. So for example, when all of the propositions are false, you will see that all of the implications are indeed true. And you can look at this again just to trace through the logic for this, but you could have also done this if you just thought through each implication one at a time. So for example, well, if P is false, okay, the first implication is true, and then you move to the second and so forth, which is what we had done in a systematic way. But once you learn the rules of inference, this will become a little bit more straightforward and not so exhaustive. So you can see how this approach doesn't necessarily work if you have more implications than this, or more atomic propositions than this. But it's a good exercise to understand what we mean for a system to be consistent. In this last section,